Okay, good afternoon. So my name is Lynn Evans. I've worked all my career with particle accelerators of one kind or another. The last one I was involved with, you may know about. I was responsible for building the Large Hadron Collider. So, of course, what I tell you will be certainly biased. So I want to talk to you about how a particle accelerator works, what it does for us in science, but also what it does for society at large. Maybe not directly, but certainly indirectly. And I'll start off, of course, very briefly. CERN itself was founded only 9 years after the end of the Second World War. It was founded in Geneva because Geneva was Switzerland, and Geneva was neutral, and it was cheap, and it's still neutral. But I mean, there were two purposes. One was to unite Europe, scientifically reunite Europe after the war, and another was to give European scientists the kind of facilities that were only available in the US and in Russia. So it was, from the start, an exercise in bringing people together, and from all over the world, and this has certainly grown enormously. And here you can see a map of the world with the users of CERN, not the people who are working here permanently, but the users of CERN. These are from the CERN member states. Observers there are 1,750 Americans working at CERN. It's the largest US laboratory for particle physics. Russia, and then a whole United Nations. You see countries like Iran, Pakistan. So it really is, its purpose is to, one of its purposes is to bring scientists together in peaceful collaboration. And I think it's been remarkably successful at that. So now I will show you a little bit how a particle accelerator works very, very quickly. The first particle accelerator was basically the cathode ray tube that was built by J.J. Thomson, who discovered the electron, accelerated a beam with a few thousand volts. And that's what you used to have in your TV screens until it became flat screen. The first real accelerator for high energy was built in the United States in 1930. This is called a cyclotron, and you can see how tiny it is compared with the massive Large Hadron Collider. You can hold it in one hand. And what you can see here, these are two Ds. These are the hollow copper D-shaped pieces. This is evacuated, of course, and a beam of electrons is introduced in the middle. And this is put in a magnetic field. And when you have a charged particle moving in a vertical magnetic field, a charged particle will bend in a circle. And this is exactly what happens in a cyclotron. You have a vertical magnetic field going into the board here. And then these two Ds that you saw, these copper Ds, there is an oscillating electric field, alternating electric field. And each time the particle crosses the gap, it gets a little kick in energy. That kick in energy gives it a bigger energy, therefore it travels on a bigger orbit. So and next time it comes back, it gets a kick in the opposite direction because it's synchronous. And of course, the orbit is getting bigger, but the speed is getting higher as well. So it always takes the same time to come around. So once you've got it synchronized, it will stay always synchronized to give a kick that way, bigger and bigger orbit until it's extracted from the machine. And that's a cyclotron. And there are many, many cyclotrons in the world today, in hospitals and in research facilities and in medical therapy facilities that I will talk about. Next kind of accelerator, one that you can actually visit here at CERN, is a linear accelerator. It works, again, with an oscillating electromagnetic field, where I'm showing a black and white picture because this is CERN's first LINAC. It doesn't exist anymore, but it's got the great advantage that you can take the two pieces apart and you can see inside, whereas a modern one, you can't do that. So it is, again, a copper cavity with an oscillating field. So the field is oscillating between these things called drift tubes. There are holes in the drift tubes, and the trick is that you have a charged particle coming in here. It sees a field in the good direction, so it gets a kick of energy. And then when the field is in the bad direction, it's inside this drift tube, so it's shielded from it. You cannot see the field. And when it comes out again, it's in the good direction again, and the bad direction is inside the drift tube. And these drift tubes, you can't see very well, but they have to be getting longer. Because, of course, as the particle gets accelerated, it goes faster, but it's got to be the same time in each drift tube. So that's a LINAC, and that is the accelerator, which is the injector, the starting point of the beam for the Large Hadron Collider, although there are a few other machines on the way to it. And now I will show you very simply the principle of the synchrotron, the really big machines that we have, research machines. The biggest of all, of course, is the LHC. And in the LHC, in a synchrotron, one bends the particles on a circular orbit. In the LHC, it's huge, 27 kilometers, by using a vertical magnetic field, electromagnets, guiding the beam around. And at one point in the orbit, one has accelerating cavities. And these cavities in the LHC are located at point 4, which is near Eschenwerder. And if you had a ticket, you could go down and see them. I spent this morning guiding in point 4. And so there's an accelerating station there. And then the trick is that the particles are going around the machine, but every time they come to the accelerating station, the field is in the good direction. When the field is in the bad direction, there are no particles. So it gets a kick. Every time it gets a kick, the energy gets higher, and then you've got to increase the field to keep the beam in the center of the vacuum chamber. As the energy gets higher, the field gets higher, until, of course, you cannot, the field is saturated, and you cannot get any more energy. And in the LHC, it's saturated at about 8.4 Tesla, very, very high field. Once we accelerate these beams, that process takes about 20 minutes in the LHC, and then we bring the beams together and we let them collide for 10 to 20 hours. Now, accelerators are a really big business. So this is a $3.5 billion sales a year, split into areas for ion implantation, industrial processing. Therapy is a big one. Radiotherapy. Isotopes, medical isotopes, which are very important. The research accelerators are very small, 1%. That's us. We are practically unique, but accelerators in general are ubiquitous. They're everywhere. Now, just to explain a little bit what we do with our accelerator, what I'm going to do now is I'm going to talk a little bit, I must say, about some of the fundamental problems that we're trying to solve here, and some of the spin-offs from them that go into greater society. So what we do here, basically, I think you're well aware of in a nuclear reactor, for instance, one converts a small amount of mass into energy. Well, we go the other way. We convert energy into mass. So we can produce the very heavy particles that existed only in the early universe. And if you want to make heavy particles, you need a lot of energy. So the equivalence of mass and energy is well known. When we talk about mass, we don't talk about it grams. We talk about electron volts. An electron volt is the energy an electron would get accelerated over 1 volt potential. That's a very tiny mass. But heat is also a form of energy. And if you wanted to accelerate an electron by 1 volt, by heating it, you'd need 11,600 degrees. It would be a pretty stupid way to do it, but in the sun, for instance, it's like that, very, very high energy due to heating. We are working in the regime of the teravolt, 10 to the power of 12 volts, and then the equivalent temperature is just unbelievably phenomenal, 10 to the 16 degrees. The sun is a few thousand. And of course, these kind of temperatures, they only occurred in the very, very early universe. And this is a cartoon that we showed to show the expansion and cooling of our universe from the Big Bang, which was 13.8 billion years ago, until now, where the temperature was unbelievably high. The temperature now is 2.7 degrees Kelvin. Not in this room, fortunately, but in the universe, in interstellar space. That is the temperature of the black body radiation that I will talk about in a minute. So over this time, the universe has expanded and cooled. And if we want to look back into the early universe, we can do it with optical telescopes. We can see objects that are luminous. They've got to be luminous for us to see them. And because the speed of light is finite, we can look back with optical telescopes about 12.5 billion years, about 1 billion years after the Big Bang. Using the cosmic microwave background, which I will explain in a moment, that was the time that before that time, the Big Bang fireball was so dense that the light inside it was trapped. And that was the time it got cool enough that the light escaped. That light is still there now, but it has expanded in wavelengths due to the expansion of the universe. And we see it as the cosmic microwave background. And that takes us to about 300,000 years after the Big Bang by studying the cosmic microwave background. The LHC takes us to 10 to the minus 10 of a second after the Big Bang, when the temperatures were so phenomenally high, 10 to the 15 degrees centigrade. That's what we can create in the LHC. So that's the Large Hadron Collider. The LHC is part of a sequence of accelerators that have been built over the many years at CERN. And this is a little cartoon of the accelerating process, which starts in the LINAC I mentioned. The particles accelerated in LINAC, then in a booster, then in the proton synchrotron, which is from 1959, then in the superproton synchrotron, which is from 1976, in two directions, because there are two beams in the LHC which collide with each other. This is the Atlas detector, and the two beams collide and produce secondary particles, which are what we study, and that could well be a Higgs candidate there. So I think that the LHC has been remarkably successful, and last year was really remarkable. It was when the discovery of the Higgs boson with a huge amount of publicity. The LHC was designed, one of the objectives was to find the Higgs boson, and we have found it. This is not a lecture about the Higgs boson. It's supposed to be a lecture about the impact on society of our work. So I'm going to talk to you about one of the other great problems that the LHC has been built to address. And this will lead directly to applications for people, and that is antimatter. This book, probably most of you have read it or seen the film, Angels and Demons, where antimatter was supposed to have been stolen from CERN, and it was being used to blow up the Vatican. I can't remember the exact story. And indeed, we do make antimatter at CERN. Antimatter doesn't exist normally, but we can make it at CERN. But our antimatter accumulator, it's not something you can exactly put under your arm and carry away. So that part of it was a little bit fiction. So we do make antimatter, and it is correct that the antimatter and matter, when they meet, they annihilate each other, and they give off a lot of energy in the way of photons. And here you can see an annihilation in one of our little detectors. What you can see here, this is a detector. You can't see the vacuum chamber, but you see these crystals. These crystals are around the detector. They're sodium iodide crystals, and if a photon, a particle of light, hits a crystal, it produces a flash of light in the crystal, and you can see that it's there. So what you see here is, forget about the the yellow thing for the moment. That's too complicated. But this red thing here is an annihilation of an electron with an anti-electron, an electron with a positron. So we put a positron in there, and there's residual gas in there. You can't avoid it. At some point, they will meet, and they will annihilate each other. And this is another of the great mysteries of the universe that the LHC is built to address, is that when we create antimatter, we create precisely the same amount of matter and antimatter. If that was the case in the early universe, in the Big Bang, then the matter and antimatter would have annihilated. And when it annihilates, it produces photons. And then you would have the cosmic microwave background. But that's all you would have in our universe. Just light, no place for us. So I think one of the huge mysteries is this very tiny asymmetry between matter and antimatter in the Big Bang that is responsible for our very existence. The tiny asymmetry that produces a residue of matter. Okay, the cosmic microwave. So the LHC is designed to try to answer that question as well. The cosmic microwave background is very interesting. I think this is a satellite measurement of the temperature of the microwave background. It's 2.7 Kelvin, I told you. And the temperature is uniform to 1/10,000th of a degree centigrade. But there are the variations are the seeds in which our stars and galaxies formed. So we are here to observe the cosmic microwave background because of a very subtle asymmetry. But let's get back to practical applications. Because, again, that is that annihilation. And that annihilation of electron with a positron, it has to obey the laws of physics. And two laws of conservation of energy and momentum. So when an electron and a positron come together, they're moving very slowly. There's no momentum in the system. So there can be no momentum after annihilation. So electron and a positron annihilate to produce two photons, and these two photons have to shoot off back to back. There is no other way. This is conservation of momentum. Zero momentum before, zero net momentum after. And you also know that the energy of the photons is going to be exactly the mass of the electron or positron, 511 kilovolt. It's gamma ray. Now, so we cannot see this line. In this detector, we cannot see this line. All we get is a hit here and a hit there, and then we can draw the straight line. Now, suppose that there was, was not an almost perfectly evacuated chamber. Suppose there was a blob of antimatter here, inside matter. Then that antimatter would annihilate back to back in all directions. So you could draw straight lines due to the hits in the crystals. You could draw straight lines, and you could detect where that antimatter is. Okay, you could detect where that blob is. And that is exactly what is done in a very modern medical diagnostic tool called positron emission tomography. Positron emission tomography works by, first of all, with a sugar, a special sugar that the body absorbs well, where one of the fluorine atoms in the sugar is made radioactive in a small accelerator, in a small cyclotron. And it's made into a positron emitter, so it will emit an anti-electron. The half-life is very, very short, 20 minutes or so, before the radiation is gone. But during that time, and if that sugar is injected into a patient, the sugar will accumulate in regions of high metabolic activity. The real power of this thing is when you combine it with a CT scan, which is an X-ray, very, very precise X-ray of the body. That's very good at seeing tumorosity. So if you superimpose the PET scan, which is showing high metabolic activity, on top of the CAT scan, then you can detect and you can differentiate between regions where, for instance, a tumor is malignant or not. And this is a diagnostic technique now that is being more and more widely used in hospitals. There's one in the University of Geneva Hospital, and there are many others around the world now. And it's interesting that the fact that antimatter was predicted by Paul Dirac in the 1920s, it was discovered in cosmic rays in the 1930s, and it's now, only now, what is it, 80 years later, it's being put to real use in our society. And there are many other examples of very, very long delays between discovery and actual practical use. Now, I'm going to now change, and I'm going to talk a little bit about the LHC, because the LHC is based on two pillars. One pillar is superconductivity, which you will have heard about, and the other pillar I won't tell you yet. So the LHC, I explained how these machines work. You need a very strong magnetic field to bend the beam around in a circle. And that strong, and in the LHC there are two beams, not one. So that strong magnetic field is produced in a LHC magnet. The normal picture, you can just see this, the blue tube. But inside that blue tube, there's very powerful electromagnets carrying very high currents, 12,000 amperes. These are the coils. This is one beam pipe, which is evacuated, of course, inside, and the other beam pipe. And these coils produce a very strong vertical field. And that vertical field is bending the beam around. And this relies absolutely on superconductivity. You cannot do it any other way. So I'll tell you a little story. Well, first of all, a bit about superconductivity. And I will then tell you about the other pillar on which the LHC is based, and a scientific mystery which nobody knows the answer to. So the first step in superconductivity was to produce liquid helium. There was a battle between Kamerlingh Onnes in Leiden in Holland and Sir Humphrey Davy in the UK to liquefy the last noble gas. Kamerlingh won that battle. Helium is liquid at 4.2 degrees Kelvin. So those of you who are not familiar with the Kelvin scale of temperature, the absolute zero of temperature, you can't go below it, is minus 273. That's 0 Kelvin. So 4 Kelvin is minus 269 degrees centigrade. So that's the point that helium is liquefied. Kamerlingh actually had a monopoly of liquid helium for 24 years. He could study phenomena in this stuff only in his laboratory in the world. And in 1911, he discovered superconductivity. He was measuring the properties of materials at very low temperature by using the helium to cool them down. And the first one he discovered was mercury. You expect metals to have less resistance at low temperature because the atoms are moving around less violently, if you like. So there's less impedance to electrons to flow. You expect the resistance to go down, but what Kamerlingh found was in mercury, it really went down to absolutely nothing. And he called this superconductivity. So he got very excited about this, and he got the Nobel Prize in 1913. And in his Nobel lecture, he said it makes it feasible, the production of strong magnetic fields using coils without iron for very high current density. It's the LHC, basically. So that's what he got really excited about. But very quickly, he had to put some water in his wine, as the French say, because he discovered the phenomenon called critical current. And the critical current is that you can increase the current, and it's superconducting, until suddenly it's not superconducting anymore, when the current is too high. He was very disappointed about that, but he made another discovery, which was very important for us, in that the critical current is higher if you lower the temperature further. He discovered that. So if you want to get very high critical current, then you cool down to lower temperature. But he missed a huge discovery that was staring him in the eyes, because he had the apparatus that would allow him to cool the helium gas to lower temperature. And the trick is the same trick as we use in the LHC. Every Englishman knows that tea tastes less good on top of a high mountain than it does at sea level. And the reason for that is that at the lower atmospheric pressure, water boils at a lower temperature. And that's the trick we use to reduce the temperature of the helium by using big pumps to pump away the vapor, and then the temperature will go down. And he was doing this every day for 20 years or so, and never, ever, he didn't even mention a phenomenon which I'm going to show you now, which is quite astonishing. So what you're going to see now is a helium which is already at 2.3 Kelvin when we start. So it's already being pumped, but then the pressure is going to be lowered. And you will see what happens when it goes down to 2.17. So just watch this. You see the helium is boiling away.
This rapidly evaporating liquid helium cools until at 2 degrees above absolute zero.
Okay? 2.17, exactly 2.17 degrees. And what is happening there is a phase transition, just like water turning into ice. And Kamerlingh never mentioned it. Why that happens is the fact that the helium completely changes its properties, and it becomes a quantum liquid with very, very strange properties. And one of these properties is enormous thermal conductivity. The reason that the liquid boils is that there's a temperature gradient between the bottom and the top. The bottom is hotter than the top, so bubbles form and go to the surface. If there is low temperature gradient, it's such a high thermal conductivity, then it can't bubble. Simple as that. So that is the mystery. It was discovered that this was a very new form of matter in 1938 only, and one of the discoverers, his name was Jack Allen. He wrote in 1988, in my PhD work in Toronto on superconductivity. You see, they were studying superconductivity, not the liquid that they were using to cool the thing. I'd often seen the sudden cessation of boiling at the lambda point. That's what we call it now. But it paid it no particular attention. It never occurred to me that it was of fundamental significance. So that's a mystery. 30 years, from 1908 to 1938, and that phenomenon was not explained. Now, that phenomenon is very important for us because in order to make the LHC magnets work at very high field, then we have to cool the magnets down using the same technique, basically, down to 1.9 Kelvin, from 4.2 Kelvin to 1.9 Kelvin, so below that lambda point. So we are working in superfluid in a very strange material with very unique properties. And that's the only reason the LHC works. So the two pillars are superconductivity on the one hand and superfluidity on the other in the liquid. I've got another little demonstration here of another of the weird properties of the superfluid. And this is basically a beaker with a ceramic bottom. And actually, we've got some demonstrations of superfluidity. If you go to cryogenics lab, I know there's a big queue there, but you'll be able to see some of these things with your own eyes. This is a bottom where the ceramic is not glazed, so it's very, very slightly porous. And when I show this now, you will recognize the transition. It's very fast in this case, and then you see what happens afterwards. So you see the bubbling. You see that phase transition? And now look at the bottom. The liquid is pouring out of the bottom. And the reason for that is that there is zero viscosity in the superfluid. It will go through the tiniest of capillaries. And that is another property that we use in the LHC. Now, the superconductor that we use in the LHC is not mercury, obviously. It is a very sophisticated, we make the coils of these magnets with a cable, which is, it's made out of strands. You can see these strands. The strands are 1 millimeter in diameter. It looks like ordinary copper wire. But if you etch away a strand using the appropriate acid, what you find inside each strand, you find 9,000 filaments. 6 microns in diameter, 9,000 filaments of niobium titanium. Copper is not the superconductor. It's the niobium titanium that's the superconductor. You can see a micrograph here of the individual filaments. So very sophisticated, and we had to make 7,000 kilometers of that. So that is the superconducting cable that goes into the LHC. And this is the effect of one of the effects of the superfluid helium. We need anyway to have the temperature low, but an additional effect, what this is here is the temperature. There are, the LHC is in eight sectors, and we cool each of the 8 sectors separately. A sector is more than 3 kilometers long, and the refrigerator is only at one end. And there are thermometers in each magnet going around the arc. There is a thermometer to measure the temperature. And you see how fantastically stable the temperature is over 3.3 kilometers with the refrigerator only sitting at one end. And it cannot be any other way. If there was any temperature gradient, the heat would flow immediately to cancel it because of the superfluidity. So that's the trick in the LHC. It's pushing superconductivity to the absolute limit of today. In your own lives, well, superconductivity, the most important use of superconductivity today is in MRI scanners. I don't know if any of you had an MRI scan, but this is an MRI scanner is a superconducting coil. So what you have here, you have a big coil around the outside, and this is filled with liquid helium, not yet superfluid. The scanners with superfluid helium are not yet required, if you like, to go to very high field. The field is about 1 Tesla here, compared with 9 Tesla in the LHC. And these MRI scanners, what they're doing basically is using the magnetic field and the radio frequency field to flip the spin of the hydrogen atoms in your body and producing these fabulous pictures, especially of the soft tissue, and like X-rays. So MRI scanners are the biggest business of all in superconductivity these days. There are some experimental transport using magnetic levitation, using superconductivity. There's one in Japan that travels at a very high speed, and one day I'm sure that these will be regularly used. Okay, so that is, I've spoken about antimatter and society. This is superconductivity and society. Now I want to talk about some other things. And just to illustrate, I will use a sheet of the Atlas collaboration, one experimental collaboration at CERN, one of the big ones. And you can see the list of the universities and institutes. Incredible list all over the world. These experiments, they have a very interesting age distribution. You can see for young people, these are where young people are being trained. What is good there is the age distribution. What is not so good is the demographic distribution. I think the ladies are still very much in the minority in the big experiments, but there's the tendency for that to change. So I think that's another thing that one shouldn't take lightly, is the importance of education of young people around our accelerators. And that's a picture of the summer students. We have them every year, coming from all over Europe and now all over the world, together to get some training at CERN. But these people, these huge collaborations have got to communicate with each other. And I think you know very well that the World Wide Web was invented at CERN, and this is the world's very first web server. I think this little box has had a profound effect on our society. I think you will all agree. There was only one server in the world in 1989, and that was in CERN. And on the sticker there, it says, "Do not power off. This is a server." Because normally, I mean, you wouldn't know that other people are using that machine, not the person at the keyboard there. So the web was an enormously important innovation in the early 90s for our previous experiments at CERN, which were on a much smaller scale. there is going to be a conference later on, I think, by Robert Caillou, who was one of the founders of the web, which you might want to go to. But now, for the LHC, a much more powerful infrastructure, at least for scientific applications, has been built. It's called the Worldwide Computing Grid. And the grid basically consists of a layered structure where there is a central node here at CERN, where all of the data from the LHC is collated. And then in different countries around the world, there's what are called Tier 1, where data storage and data analysis is made. And then there are Tier 2 centers, which are then sitting in universities, where people can access LHC data at their computers, not knowing where the data is coming from, not caring. That's why it's called the grid. Your electricity, you haven't got a clue where it's coming from. And this is a massive computing infrastructure now, with 2 million jobs per day, 250,000 CPUs all around the world. Now, whether the grid, what impact the grid will have on society in general, we cannot say. We were very naive with the web. But certainly in areas where manipulating a large amount of data is needed, like we have to, like climate research and medical research, etc. Already there are many other people now jumping in on the bandwagon using the grid technology that we have created for the LHC and producing this massive infrastructure that we absolutely needed in order to in order to analyze the data from the LHC. Okay, finally, I'm going to talk about some medical applications. I've already spoken about one, but one application, of course, is hadron therapy using the particle beams, and I will explain why that is that is much more effective than other forms. The imaging part, I think I already mentioned the positrons, etc. But for tumor treatment, the conventional way is using X-rays or gamma rays, gamma knife, to irradiate tumors and to kill the cells. But when you do that, then this is the dose. This is water, but it can be a human being as well. But when you do that, to get a dose at the site that you want to, then you are giving a dose everywhere, and in some places a much higher dose. And after the site as well, you're giving a very big dose. Whereas if you use a proton beam is the nucleus of a hydrogen atom, okay, the ionized hydrogen atom. And then there is a phenomenon called the Bragg peak, where a proton going into material is stopped at the very end of its energy. That's where the major deposition of energy is. So you see, when you do therapy with protons, then you get a much lower dose at a depth which you can determine by the energy of the protons. You can move this peak anywhere you want by varying the energy of the protons. And then you get a very high dose at the point that you want. And you can scan this back and forth by varying the energy of the machine itself. And it's even more effective if you use carbon. Instead of protons, which are just one nucleon, carbon-12, you can also accelerate. And then, because it's heavier, then the Bragg peak is higher and even narrower. So hadron therapy is now a very important part of the armor in fighting cancer. There are a number of facilities around the world. I just took a couple of random examples. This is one in South Africa, actually, which is based on a cyclotron, similar to the one I mentioned right at the beginning. And then, there is making radioisotopes is one thing, like the sugar that you need to do a PET scan, or radioisotopes for many other applications, mostly medical, but not only, and for doing hadron therapy and actually treating patients. And there's another one in Heidelberg in Germany, which is actually accelerating carbon instead of protons. That's now operating with patients, and there are several more under construction. So hadron therapy is another application of accelerators, which is now becoming very important. Now, I could talk for a very long time about many other applications. I will just tell you one more, and that is the use of synchrotron light. When we bend our particles in a circular orbit, they give off light. It's called synchrotron light. And if you bend very light particles like electrons, then it gives off a lot of light, and it makes them very hard, actually, to accelerate, because the higher the energy, the more light is given off, and that energy has to be replaced into the beam. With protons, is much, much less synchrotron light, so we don't have a problem in the LHC. But that synchrotron light is a nuisance to us when we want to get up to very high energy with electrons, but for others, it is a marvelous tool, because one can build light sources. It's a synchrotron, just as I said, with electrons going around. And then you can get, the light comes off tangential to the beam, so you can put these beam lines around. And then you have a collimated beam of X-rays. You can define the frequency that you want, but a very collimated beam of X-rays, and that is used for material science, for unraveling the structure of proteins, called complex molecules, and for many other applications. And there are 50 synchrotron light sources in 29 countries in the world, with about 60,000 users worldwide. So that's another very important application of accelerators. So I'll just finish off by emphasizing what the mission of CERN. I think our mission, of course, is first of all to do fundamental research. That's for sure. To find the Higgs boson, to understand the asymmetry between matter and antimatter, to understand dark matter and dark energy. I've not said anything about that to you. To really address these very fundamental problems. But also, I think, in doing that, we develop things like the World Wide Web, things like the software to analyze the PET scan. It came actually from CERN. We develop tools which can be useful. We train young people. I think that is an important contribution to society as well. They come and they get trained in an international environment with a very demanding, and we bring nations together in peaceful scientific collaboration. And it's incredible, the mix that we have here at CERN that would never work anywhere else. So I think that's what we do. In spite of our great success, we are continuously being asked to justify ourselves. Who cares whether we found the Higgs boson or not? I mean, the fact that we found a fundamentally new field pervading all space that we didn't know about before is a huge step forward. But I like to finish with a couple of replies about the importance of fundamental science. The first one is very interesting because it comes from a 19th century mathematician, Jacobi. And he said, the sole end of science is the honor of the human mind. Now, I can tell you, if you go to a funding agency in your country and ask for money with that as an argument, then you won't get very far. But I think the real pertinent one came from a source which was quite unexpected, and that was the Iron Lady, Margaret Thatcher. She said, the greatest economic benefits of scientific research have always resulted from advances in fundamental knowledge rather than search for specific applications. And I think that is actually the case. We did not set out to invent the World Wide Web. I think it was a need. And I think that is the best justification for what we do of all. I hope I've explained to you a little bit about the impact on society of accelerators. And I'll stop there and answer any questions that you have. Thank you. So do you have any questions? Yeah? Can you press the button, because this apparently is webcast. So.
Okay, thank you. I want to know, how does CERN finance themselves, and how is the economic impact for the society? Like if you, I think CERN is built with the fundamental industries who supply any equipment, and has an impact to the industry in the supplier countries.
Well, how is CERN financed is it is financed by a contribution from the member states. There are 20 member states of CERN that pay the CERN budget according to their net national income. Okay. Of course, CERN has a lot of impact. Building the LHC, there were contracts all over Europe and all over the world, putting contracts back into the countries. So it has got an important economic impact. These contracts also lead to other contracts in many instances. So there's a multiplying effect. And our technologies, of course, are freely available. I mean, the web was free for the whole world. Any other questions? Yes?
Yes. When you listen to scientists such as yourself and people like Brian Cox and so on, they always talk about the inspiration they received by watching things like the landing of Apollo on the moon and so on and so forth. So I think what CERN is doing here is very inspirational. And what is CERN doing to pass on some of that sense of excitement and inspiration to school children, yes, young children?
Yeah, well, I couldn't agree with you more. I think that I think that a real spin-off of these kind of flagship projects is inspiring young people. And I mean, it's more than anecdotal. In the UK, for instance, the input into the hard sciences has gone up 20% in the last 5 years or so. And this could be the Cox effect, it could be the LHC effect. It's certainly a combination. And that's essential. We do need many more young people scientifically educated. They're not all going to come here and do research, but even in industry, we need a lot. So the inspirational effect of a big flagship project, I think, is not in doubt. There is also another inspirational effect, and that is good teachers. And that's what we work very hard for. I work with kids, but you can only do so much. The added value is much bigger when you work with the teachers, and you try to inspire the teachers, and they, the multiplying factor there. And that's why we have every summer we have teachers coming here, as well as summer students. We have about a few hundred teachers, and they come and spend about a month with us. So yes, that is not a tangible thing, but I think it's certainly very true. Yeah.
So the LHC was the upgrade of the CERN Accelerator complex. And I guess there is still a plan for the next 10, 15 years for working of LHC. How is the complex going to be upgraded next?
The LHC, well, let me go back to 2008. I think a lot of you remember that when we started up the LHC, we had a problem, and the problem was with one of the splices, the joints between magnets were done in the tunnel, and there are 10,000 of them, and one of them failed. That in itself wasn't a big deal, 1 in 10,000, but it produced quite bad consequences in overpressure, etc. So because of that, the LHC energy has been limited to 4 TeV, not 7 TeV as it's designed for. until we could stop and then inspect all of these joints, among other things. So the LHC has run for 3 years. It's found the Higgs boson. We've got a huge amount of data to analyze. So now we can stop and consolidate. And that's what's happening now. That's why we can have this open day, is that we are shut down. We will be shut down until about the end of next year. And then when we come back up, then we will take the machine to its full energy. Of course, I mean, you know, it was already plenty of energy to find the Higgs. But now we want to go further. We must investigate the properties of the Higgs boson, find out if there are any other Higgs bosons, and try to get to grips with especially the issues of dark matter and dark energy. These are the real big questions that I hope the LHC will answer. So that's what will happen. End of next year, we will come up at nearly twice the energy. And then we'll see what it will give us. Any more questions? Yeah.
Is there any particle you believe to find first?
Is there any?
Any particle you'll believe to find first after the Higgs boson?
After the Higgs boson?
Yes.
Well, what we are looking for, I mean, first of all, this is research, so we might get a complete surprise. We found a Higgs boson. There are some theories of what this dark matter could be in our universe, and if one of the main theories is right, there's not one Higgs boson, there are 5. So we will see what the LHC tells us as we go up in energy. As we get, if it's heavier, then you need more energy, and so we can. So we will investigate the properties of the Higgs boson, what else is there, and take the machine up to higher energy, and really try to get to grips with these questions, especially the dark energy, dark matter, and dark energy.
Sorry, one more.
Yeah.
Can you explain what is supersymmetry and what the CERN is looking at concerning that?
Yes. Well, just like there is the world of matter and the mirror world of antimatter. Okay, every matter particle has got its antimatter cousin, or whatever you want. We can create antimatter in our accelerators. For every particle that we know, we can create its antiparticle. Now, there is a theory called supersymmetry where and the matter is made out of 2 kinds of particles, fermions and bosons. And there is a theory that there is another mirror world of where fermions in our world become bosons in that world, and the bosons in our world become fermions in that world. If we can create that, and the lightest neutral particle in this supersymmetric world could be responsible for our dark energy. Because dark energy, it means that there is a gravitational force, but there is no interaction other than gravity as we know it. So that is supersymmetry, that there is a mirror world, just like the world of antimatter. And that is the world we are going to try to create when we come back up. We haven't done it yet. Okay? Okay, thank you.